All right, welcome everyone. Week 10, day 2. We're going to be talking about the Quake nail gun today because Dolio got a copy of the Quake 1 soundtrack composed by Trent Reznor of Nine Inch Nails, which is why there is a nail gun in the game and why you can find Nine Inch Nails as ammo in the game. It's pretty cool. Pretty cool stuff. All right. So, let's see here. So your sepia toning thing is due tomorrow at midnight. So make sure you do that. And submit 2 photographs, one of Kyoto, one of any other image of your choice, and have the running time be for Kyoto, obviously. Yeah, so I will award extra credit based on how fast your implementation is. Now, your next and final image processing assignment is going to be on maybe the last, maybe the final. I might do one more using bridges, which is to make an artistic image filter in ARM assembly, either ARM assembly or Neon, either way. Okay, so we'll just go over a little more on Neon, just because I know people want more help with that. Nan is greater than Nin. Walk up, can you hear me now? Hello, testing, testing. Is it all good? Yes, we'll just do a few more. We'll do a few more slides over using Neon and working with floats and things like that. Then you guys, yeah, more Neon examples, yeah, exactly, because it's basically anything you can do in normal ARM you can do in Neon, kind of, except Neon can do single precision, double precision, ints, signed, unsigned, so. It's kind of better, especially if you're going to be processing lots of numbers at the same time. You want to be using Neon if you want speed. All right, so the Raspberry Pi 1 had what's called Vector Floating Processor version 2, and it had 32 single precision float registers named S0 through S1, and it had double registers D0 through D15, which are the same thing as S0 through S31. VFP version 4, which is on the Pi 2 and the Pi 3, and I believe the Pi 4 as well, unless they updated it. I haven't checked. It has 32 doubles, so it has twice the number of double registers. So what's really nice about that is that you can use your normal 16 integer registers, of which 8 of them are kind of off bounds for using in variables. So you got either 32 doubles, or you can have 16 double registers, 64-bit registers, and 32 32-bit registers, in addition to the 16 basic ones. And so you can just use them as regular registers if you want. That's fine. Nobody's stopping you. And so if you ever run out of registers on, just your normal R7, R8, that kind of stuff, they're there. They're available for you. Just be aware that the D16 through D31 don't have single precision names. So you can't refer to them by like single precision 40, for example, does not exist. So single precision 0 through 31 overlaps D0 through D15, and then the remaining D registers, double precision registers, can't be addressed in 32 bits. All right, so here is a regular load, right? So if you've got a, if you have, let's say down in the data section, so remember the data section is not complicated, you just say data, and then everything after that is considered data, and it gets put into the data chunk of your program. And so if you have like a variable name there, down there called, let's see, it would be .word pi 3.1415 or whatever. Or it's .float, yeah, whatever. Float. If you want to load this constant into a register, the first thing you do is you load the address into a register. So equals pi is the address of this variable here. So we've got a variable down in the data section somewhere. Where's my mouse? There it is. And so we need to get the address of that. That might be address 0, 5, whatever, some memory address, and that memory address of pi goes into R0, and then we load from R0 into a single precision floating point register. So there's 2 steps to load numbers like that from the data section. You load the address first, and you load from the address. You might notice that one is a regular load. So this is just doing a regular load because we're in regular ARM world over here. And that just puts a 32-bit pointer into R0. And then we load from R0 into the neon registers. This is a vector load. So yeah, there's a V there. Basically, everything you do in neon is going to have a V in it. Okay. So it's a vector load. So it's going to load 3.1415 into single precision register number 5. And why does it say S0? It's strange. I'll just make you S0. That's it. So that it matches the comment here. Okay, load. So if you have a double named 2, this will load the address of 2, and then this will load it into the D5 register. Okay. And so S5 is going to be what, D3? So these are actually going to be able to coexist. Or we aren't doing S5 anymore. We're doing S0. So yeah, so these 2 guys can coexist just fine. You just have to be careful when you're mixing and matching single precision and double precision registers because they're the same registers, just named differently. Okay, and then you can also just do this. If you want to do a single command load, you can just pass in that. And this only works, though, if 2 is in the text segment instead of the data segment. So if it's in the data segment, you must LDR it. If it's in the text segment, then it can just put the value directly into D5, which is faster. It's 1 load instead of 2. LDR loads the memory address for pi, then VLDR loads the value at the memory address. That is correct. Yeah. Dereferencing a pointer. Okay. So, and I think I discovered that by accident from doing it wrong and having it actually work. Okay, so copying from a float into a register. So if you want to move it back, so let's say you've got all of your neon stuff done, and you want to print it. When you pass a double to a function, it's still passed using R0 to R3, and so these are your function parameters, right? R0, R1, R2, R3. So normally you can pass 4 variables to a function. However, this is not the case if you have a 64-bit number. You have a 64-bit number. These 2 guys are the 64-bit number. These 2 guys are the second 64-bit number. Okay. So if you're passing a 2 doubles, the first double is going to be R0 and R1. The second double is going to be R2 and R3. So you can only pass 2 doubles to a function. Okay. Yeah. Okay. So this will move from. So if you want to copy between an R register and a neon register, you use vector move. And this will just do it's not really a vector move. It's just everything in neon is named with a V, right? So this is going to move the value from R6 into S0, and then this does the opposite. So this moves the value from S0 into R6. So this is how you can copy to and from single precision registers into regular registers. And I think we talked about last time, if you're going to be doing a double, then it moves into 2 different registers. So you do something like this. Vector move, R0, comma, R1, double 0. And that will move from R0 into R0 and R1. So you pass a pair of regular registers whenever you're moving to and from a double. And can you do this with a quad? I don't think so. Quad registers are used basically only for vector operations. Doubles are actually, you can actually multiply doubles and add doubles together. They're actually, basic data types. You can't, there isn't actually a quad word thing. Like, you can't do 256-bit math, unfortunately. It'd be nice if it could, but The quad registers are 128-bit. The quad registers are only used for vector operations. Why not? I know. Just because 64 bits is enough for anyone, Dolio. That's why. But I'd agree. It'd be really nice if you could do 128-bit floats or 128-bit ints. Yeah, why not? If you're going to multiply two 64-bit numbers together, the answer is going to be 128 bits. So, okay. Yeah, one day. Right? Yeah, one day. And then, in the Intel world, you've got AVX 512, right? Which does 512 bits at a time, which is pretty cool. Pretty cool stuff. All right. Be careful that this is just going to be a pure bit copy, right? So if this is in the IEEE 754 format, this is going to just put the bits of a float into R6, and if you try counting it as an integer, it's not going to work. You can count it as a float, because it is a float, but you can't count it as a integer, or it will look really weird. So if you wanted to convert it, you can do this. So there's vector convert. So this converts from a 32-bit float into a 64-bit float, and that will move between, it's another way of moving between registers too. So this is going to move the value in S6 into D0 and widen it to be a 64-bit double. If you want to narrow, if you want to move the value in D0 into S15, and this is going to narrow from, it's actually going to truncate also. So it's going to go from a 64-bit float into a signed 32-bit integer. So if the number was 3.1415, it'll now be 3. Okay? So you can convert back and forth between 32-bit floats, 64-bit floats, signed, unsigned integers at different widths, things like that, using vector convert. That is your casting. This is how you do casting between different types. Okay? Remember, in the R world, everything's just considered to be an integer. Signed, unsigned, it doesn't matter because 2's complement works the same way, either way. Okay. And so this would convert from a 32-bit float into a 64-bit float, convert from a 64-bit float into a signed 32-bit number, and then this would move it from the S register into the R register. We don't need more than 640K of RAM. That's right. It's plenty for everyone. All right. So, if you want to copy a float, okay, you wouldn't copy a car, would you? Anyone know what movie that's from, out of curiosity? Testing your cultural literacy today. It's a movie, yeah. You can tell by the potato quality of the graphics. It is the ending of one of the most famous comedies of all time, named Animal House. Yeah, Connor McLaughlin got it. 10 points to Gryffindor. Oh, wait, we're not doing houses this year. Yeah, normally in this class, you'd be divided into houses, and you'd be getting points, and the points translate into extra credit. But sorry, no extra credit for you guys this year. All right. Instead, you're getting just extra credit on literally like almost every homework assignment. But in order to get the extra credit, you guys got to make your code fast. So it's gonna make up for the missing house points. All right. So if we are going to add two floats together, then vector add is how you do it. And remember, when you're working with Neon, you always have to provide a type. So Neon adds types to assembly. In regular ARM32 assembly, there's no types. Is it signed? Is it unsigned? Who knows? They're just bits. And with Neon, basically anything where it matters what the type is, you have to provide a type to it. So we're doing a 32-bit float add between S1, S0, saving the result into S2. Subtraction, same way. So here is a 64-bit subtraction. D1 minus D0, result is saved into D2. So for your next homework assignment, the one that's artistic, these are all your tools that you can use. Okay. Multiply, 32-bit multiply, 32-bit divide. Yeah, we got divide. Cool, awesome. Absolute value exists also. Square root exists, so you don't have to use the fast inverse square root. But fast inverse square root's probably going to be faster. That's why it's called the fast inverse square root. So, yeah. So if you want to square root something, it's real easy. What is the syntax for .float pi 314? It's that. Just stick that into the data section. Okay. And if it's wrong, then let me know, because if I don't use something recently, it's one of those things where I'd have to dig into my old source code and check. But it's not compiling. All right. In that case, we will. Wrong server. Pi.float 314. Okay. That sounds right. So pi.float 314. Okay. All right. You can only do floating point comparisons in the AFP. You can only do branch statements in the normal CPU. So, really important thing here, right? So, if statements are only done in regular ARM assembly. And so if you want to compare two floats, say like, is one float bigger than another, or is this number greater than pi or less than pi or something like that, you can do a comparison. There is vector comparison. And we're doing a 64-bit vector comparison between D6 and D7. And again, it will do less than and greater than or equal to, and less than and equal to spaceship operator, basically. But the results are not available. The results are not available to doing a branch. So every time you do a vector comparison, you have to follow it up with this magic word here. Okay. And it is magic. That's my magic wand right there. Okay. So remember how we talked about there was a CPSR, like this control program status register. It's basically copying the results of the floating point status control register, I think it stands for, into the CPU's regular ones. Basically, this is a magic word, meaning make the results of the comparison available to the regular CPU, which is just a pain in the ass. You have to do that. And then after that, you can do a branch. So, and conditional things work. So you can do vector add if greater than, that works. Branch if less than, that works. So all the usual tricks and stuff like that works. I don't think set works. I don't think you can do a vector add in set. I don't think that works. I'd have to check it. Or maybe one of you guys can check it while I'm lecturing here. See if you can do a vector add with a set on it. I suspect it won't work. Okay. Yep. So that's how you do if statements. So it's the same thing you always know. There's just one little bit of magic here. So don't forget, like I always do. Why is my comparison not doing anything? Because you need vers, apps, should have just made it like one command, like just copy, or I don't know. It's kind of annoying that that's what they picked. The ARM language has gotten progressively less human friendly over the years. When it first came out, it's very easy. Like you guys like picked up assembly coding really fast this year, you know. And, it's not really that hard. The hardest thing about assembly is just kind of debugging it when it doesn't work right, because you don't have the same ability to print things, and so you kind of have to make helper print functions. But if your variables are in the R0 through R3 range, then the print function destroys your registers, and it's like it's just kind of annoying to work with. But it's not hard, right? Like, would you guys agree with me? Like, assembly's not hard. Not having named variables, yeah. You can name like things like pi and stuff like that. If you don't have constants, you can do that. But yeah, that's why usually when I'm writing code, you can use macros also. You can use a macro to kind of make your code tidy a little bit. But yeah, for me, whenever I'm writing assembly code, I'm doing like, I got my add R7, R1, R3, and then I'll put a comment after it saying this is X is equal to Y plus Z, or whatever. Like I document my assembly code with the C++ code that it's doing. You know what I mean? And so that's an easy way for me to just keep track of which one's X and which one's Y and which one's I and stuff like that. Yeah, it is kind of annoying though. Yeah. It's not hard getting things to work. It's hard to make things efficient. I mean, yeah, but like making things efficient's like the fun, or at least it is for me, right? Because like for 3 semesters now, you guys have just been like, just get it to work, pass the test cases, and now like it's like, all right, make it fast, and once you really start like putting your foot on the accelerator and like trying to really squeeze performance out of something, like you can see what a massive difference like a well-optimized assembly program, like what was it, like 6 seconds for the sepia toning, I think. Like if you use the CImage library to do it, it's 6 seconds to sepia tone Kyoto. And even with reference, even with like dash 03 and all of the tricks turned on, like F-tree parallelize, all that stuff. Is it not built? Great, cool. What's going on here? Did I break my make file? Am I back on wrong host name? Localhost. That's helpful. So the CImage library, which has the ability to do image filters in it. When I wrote the sepia image filter and using the CImage library, it was 6 seconds to process Kyoto. When I squeezed all the performance I could have out of C++, it was like 1.5 seconds, something like that, at 1.3 seconds. And so this is 0.02 seconds. So you can see just how much faster you can really squeeze something if you put the time and effort into it. Okay. And I've rewritten my sepia toning filter a lot of times. And there were things that I thought would be faster due to pipelining. And once you guys understand pipelining, then it's like, okay, all right. So all right. And you understand superscalar and there's dual issue and dual retirement. So I can do 2 loads at the same time and get both those guys going. And while that's loading, I'm going to do these other things that don't depend on the results of that load. And then I'll use the results of the load after. And by really sitting there and like playing with the stuff, you can really squeeze the hardware to get as much performance as you want. And like I've said many times, you're probably not going to be a full-time assembly programmer. You might not even write assembly after this class professionally. That's possible. But all of these techniques you guys are learning to squeeze performance and things like that out of the hardware, it's going to help, all right? Your next assignment after the artistic one, your next one is just going to be on Tuesday. Just make an art filter. You're going to be graded on the artistic merit of your image filter. Okay. So, do anything. It's basically free points for you guys. Pick an image, make a filter. We'll just be due on Tuesday. You can work with a partner if you want. I don't care. And yeah, if you work with a partner though, each of you have to write a filter. And then you're going to composite the filters together. So you're going to load an image, run player 1's, partner 1's image filter, then run partner 2's image filter on top of that. Okay. And then just submit it on Canvas, and it's just easy points. Like all of you guys should be able to do it. It's not hard. All right. All right. So yeah, let's just go through the rest of this. So you do comparisons. You got add, subtract, multiply, divide, absolute value, square root, comparisons. And then doubles, yeah, so normal pass, so doubles can get passed in via D0 and D7. This isn't always the case, right? So if you're like calling printf, printf is going to pass in, like, printf takes a string and then a parameter, right? Or X number of parameters. Maybe 0, maybe 1, maybe 50. So if you try printing f again double, what happens is the string itself, the double quote percentage f, I think f's double, is the first parameter that goes in R0, and then the double gets passed in R2 and R3. Okay, so when you mix regular and double parameters, then, like I said, the doubles take up 2 parameters. Doubles get passed in only in pairs R0 and R1, R2 and R3. But if you have a function that is pure double math, then it passes in up 8 parameters, all using the D registers, and it returns the result in the D0 register. So if you ever want to look up the documentation, that link there has what's called the ABI, the application binary interface, that explains how functions call each other. And this is actually a really important thing. This is an important term for you guys to know, because one of the big things holding back hash tables, why do hash tables in C++ suck? The reason why hash tables in C++ suck, and everyone knows they suck, and are bad performance-wise, is because if they were to change them, it would break the ABI. And so so if you have a compiled library that uses an unordered map in C++, and you called it with a fixed hash table, it would break, it would be an ABI break, and they won't do it. Like, the standards committee is in this weird sort of limbo where they haven't actually said that, if it's against the rules to break ABI, but there's a lot of C++ libraries out there that are compiled and are only available in compiled form. And so if you're expecting the hash table to look like this, and it doesn't, it's got different functions or whatever, or the bytes don't line up right or whatever, so far the C++ committee has been avoiding doing anything that breaks ABI, or trying to avoid doing anything that breaks the ABI. And so how something gets passed to something and how something accesses something, there's kind of a standard. And in this case, we're talking about the ARM procedure call standards, the AAPCS. But overall, the term is called ABI, and that's how things talk to each other in binary, not in the language, not in C++. Because it'd be very easy to update the unordered map in C++. What does that mean? Like, remember how in CSci 41 we talked about how there's like an interface? There's an API. So as long as you call insert and search and remove and that kind of stuff, and you don't look at the internals, then I can rewrite my hash table however I want. And that's absolutely true. But the trouble is, if you pass one of those new hash tables to a library that takes one of the old hash tables, it'll break. And so that isn't an API issue, it's an ABI issue. And people are upset about it because that's stopping progress, you know what I mean? Like, it's like, we could fix this and make them faster. Like, we all know it could be faster. But to do so would break it. And so some people have just proposed unordered map 2. Right? It's just a new hash table, you know, it's better than the other one. Hash table fast, you know. That's what they did with smart pointers. Rather than fixing smart pointers, they came out with new smart pointers. So there used to be something called auto pointer, and auto pointer turned out to be irrevocably broken. And so they came out instead with unique pointer and shared pointer and weak pointer. And if hash tables are so great, why isn't there hash table 2? Hash table 2, electric boogaloo. Yeah, because it's like, it should just be a replacement for it. So people want to just get rid of the old one and put in the new one, because the interface is the same. If all you do is compile your code fresh, you know, make clean, it'll just work. But if some of your code has .o files, right, that has the old hash tables in it, and you include the new hash table, they won't talk to each other anymore, and it'll explode. And so this is actually a really serious issue in the C++ community. And so one proposal that's out there right now is called epics. Not like the loot you get from, you know, the purples. This purple, it's an epic. Epochs. So they're actually proposing having epics in code. And so when you compile your code, it'll be like, I'm compiling my code to the C++ 11 years. And so make my hash table not the new one, make it the old one. right? And so you could have backwards compatibility if you wanted it. And so that's a solution. But what that's going to mean is that the compilers are going to have multiple versions of the hash table class, right? So if you've got two different hash tables, then it's going to use different code for, if you compile with the older epic or the newer epic. And it goes beyond that too. Like they're saying, like, in a new epic you can be like, nah, like all this old stuff that we shouldn't be using anymore goes away, right? So all this cruft that's built up over C++ over the years, it'd be like making C++2, and so you can compile it under C++2 or under old C++ classic, WoW classic. But then people are like, that's going to bifurcate the community. Compilers aren't going to support them equally. So people that are using the old epic stuff, because they got, like, a lot of people are stuck using the old stuff because all they have is a .o file or .so file, which is more or less the same thing. .a file, which is more of the same thing as a .o file. They don't have the source code. They bought a library from somebody and they have a .a file that's a collection of .o files, and that's all they got. And their business depends upon it. And the company that sold it to them is out of business and aren't releasing updates anymore. And so if they are going to bifurcate the community and have new Coke, C++, and Coke Classic, they're not going to be supporting Coke Classic as much anymore. Bugs are going to crop up. It's a big mess. And so, aren't there already two different C++s? Yeah, well, there's right now we have different versions of the standard, right? But that's not exactly the same thing. If you use C++ 20, the unordered map in it is fully compatible with C++ 11's unordered map, right? So it's the same class. If you compile a .o file under 11 and under 20, they can talk to each other. But if they were to update the hash table, then a C++ 11 compiled .o file wouldn't be able to talk to and link with a C++ 20 .o file. And that's something that's a big controversy right now, like how to fix that. So the solution is right now, make your own hash table, right? Like, don't use unordered map if you care about performance. Now, as it turns out, unordered map is fine, right? Like for, for work that I do, I just use unordered map and it's fine. But, it's probably, I don't know. I don't remember the exact ratios, but it's a lot slower than it could be. And people know this, and they're just like, make your own, or, find somebody else that made a hash table and use that one. Go on to GitHub, So far, they're just ignoring it, is kind of what they're doing. C++ and Java are improved versions of C++, yeah. Yeah, Java is really, Java is kind of a safe C++. Like Java came out during the mid-90s, where every week there was a new security vulnerability caused by C and C++, because it did not do bounds checking, and there was no ASAN to do bounds checking. And so the Java language was like, pointers suck, because pointers don't have a range on them, right? Because a pointer to an object's fine. Java has pointers, they're called references. They have pointers. But when you pass a pointer that's an array, you don't know where the end of it is. And your code can't tell where the end of it is. And so they just basically made a safe C++ that would bounds check everything. If you go out of bounds in Java, the runtime detects it and kills your program. So that's what Java was really based on, because, if you're a bank, you don't want to have the hacks. It's really important. And for years, the old-time programmers like me, except I never said this, just told people, get good, scrub. Like, that was the official response from, like, the GNU people, right? So the people that made GNU C, the compiler, they resisted, like, changes that would make the language safer, or compiler add-ons that make the language safer. They were just like, get good. That was their answer. Get good. Don't make mistakes in your code. And as it turns out, that approach didn't work. Like, nobody turned out to be smart enough to find all the bugs. You had some of the best people looking at it, and the thing is, like, dealing with strings, especially in C, turned out to be a really, really annoying problem. A really, really, really annoying problem. And so, and then I went to a talk a few years ago, and the guy ran Ubisan, the undefined behavior sanitizer. They ran it on the GNU C compiler and found like 1,000 different places in the GNU C compiler itself that used undefined behavior, that had undefined behavior in it. So undefined behavior isn't necessarily a bug, but it could be because it's undefined. Who knows? You know, you can anytime there's undefined behavior, the compiler could emit any code it wants. And so the fact that it's working is not a guarantee it's always going to work. So if there's undefined behavior, it could just delete the code and not do anything, right? And that includes things like addition, like A is equal to A plus B. This is undefined behavior potentially. Why? Because the numbers could overflow, right? And overflow is a, what is it? Unsigned overflow is defined, but signed overflow is not. Or I might have that backwards, but I'm pretty sure that's correct. Because 2's complement was not the standard. And I think in C it's still not the standard. And so you can't actually guarantee what happens when 2 signed integers overflow. And so the compiler is well within its rights to be like, "Niet," and just not do it. And that would break everyone's code. Because, you know, you just have integer A, integer B, and you're adding them. "Niet," undefined behavior, right? So, yeah, it's a problem. And so what the compilers do is they'll just generate an add instruction. Like this will, in practice, what the compiler does is, where's my mouse? It'll just generate an add R0, R0, R1, or whatever. You know, it'll just make an add for you. But in reality, you could just delete it. And there have been some really serious security vulnerabilities that came about from the compiler deleting code. Like if there was a check for a null pointer, the compiler would delete it because it would know that the pointer can't be null, but the pointer could be null, and so it would delete the check for null. And one of Google's most serious security vulnerabilities came about from a null pointer bug from a check they had in their code. They had in their C++ code a check for a null pointer, and the compiler was removing it due to the way that undefined behavior works. So, yeah. And so this professor, you know, he sent a list of the 1,000 or so problems with the GNU compiler to the people that told everybody to get good. I don't know if you heard back from them or not. But that was a really good talk. And if you guys are interested in that, because undefined behavior is a big issue. What was his name? I talked to the guy too. Utah undefined behavior. Yep. Ldr PBCon 17 maybe. I'll swear Ldr. Sorry if he's watching this. Ldr. Yeah, okay, that guy. Yeah, he's pretty awesome. So if you undefined behavior in 2017, John right here. So you can find the talk. Most of the CPPCon talks, not all of them, but most of them, are on YouTube. Undefined, yeah. So I'll put the link to that in Discord, and that's a really good talk. And there's 2 parts to it, and it will. Especially if you guys are planning on becoming professional programmers, which hopefully, it's really good to know what undefined behavior is, because there's a lot more undefined behavior than we think. And nowhere in the standard does it have a appendix or whatever, a table of all the different kinds of undefined behavior. Instead, it's just kind of scattered through the standard, right? If you add 2 of these together, it's undefined behavior. But it doesn't even use the same terminology every time. The result might not be known or something like that. And so they had to write like a search tool to dig through the, 1,800 pages of the C++ standard now, something like that. It's a big ass standard. And they had to find all the different ways they phrase the word undefined behavior. And they built their own like canonical list of all the different things that can shoot you in the foot. Put up your McDonald's application, not feeling the CSI thing. After this class. After this class, yeah. Okay. So, wow, that's a lot of neon. Okay. All right, so neon, vector load. Yeah, so do you guys have any questions about undefined behavior? Because I know I do. It's, yeah, sitting in that audience, watching all these, like Marshall, who was the guy that writes the standard library, one of the guys who writes the standard library, he's a cool dude too. You know, like there were a lot of like top tier C++ people, and I wouldn't consider myself in that because there are people that know the standard 1,800 pages really well, and I don't, because I frankly don't care about the nooks and crannies of the language that much. I try to write easy, readable code that works and is bug free. That's my deal. And these people are like, whoa, that's undefined behavior? Yep, it's in the standard. It's undefined behavior. So technically, the compiler do whatever it wants, like Hartman. So, do you think it's possible to remove it? To remove what, Connor? Remove what? Undefined behavior? No, undefined behavior is good. See, here's the thing. Like, it's actually good to have undefined behavior in the standard. What? Yeah. The reason for that is this. They can't, until recently, mandate that, like, 2's complement, right, was the standard. The reason for that is because, let's say you use a CPU that doesn't use 2's complement. If the C++ standard mandated that 2's complement be mandatory, so that signed integer would be defined behavior, then what would happen is if you're on a CPU that doesn't use 2's complement, the code would become very, very inefficient, because every time you did an addition, it would have to check to see if overflow occurred, and if overflow occurred, modify the bit patterns to match 2's complement, because it would not match the native format in the CPU. And so undefined behavior allows the compiler to delete stuff to speed up code. So undefined behavior is wiggle room for the compiler to optimize. Or, yeah, that's one way of putting it. Or so that you don't have to check for certain conditions, right? If you say, like if you mandate that it throws an exception anytime there is integer overflow, then every time you do an add, you must follow that with a check for carry set. And if carry is set, throw an exception. So every time you do an add, it's now 3 lines of code, right? And it will drastically slow down your code. So having undefined behavior gives you, it's actually a good thing to have undefined behavior. The trouble is when you write undefined behavior as a programmer and you're not aware that it's undefined behavior. Then the compiler can do something completely different from what you think is happening. That's the problem. And it's not well documented what is and what isn't. So I highly recommend all you guys watch that talk I just put on Discord. It'll blow your mind. He's a good talk too. He's a friend of mine actually went to the University of Utah, and I think maybe had him for a class. He's a cool dude. Like I said, I talked to him at the conference, and he's a really nice guy. So being aware of that is really useful. Did my coffee arrive? Can you check? Door-to-door coffee service. Okay, so yeah, so you actually want the standard to have undefined behavior in it, as weird as that sounds. Okay, so let's talk more about Neon. So this will do a quad. It'll load 128 bits. It'll load from this memory address into a quad register. This one loads 256 bits with one load, and it advances the pointer by 256 bits. So that's really nice. So that's what, 20, what was that? 32 chars all loaded in one instruction. Okay, pretty nice, pretty nice. This will do 16 shift writes. I think you guys have done this one already. So that will do 16 shift writes. So the quad register, which is made of 16 chars. How do I know it's a char? Because there's a type on it right here. Shifts all of them right, and they don't overflow into the next channel, which is really nice. So you can load more than one quad register. Yeah. As it turns out, it's not faster. Spoiler. Yeah, I tried many different ways of loading, because I found the bottleneck actually just being to read the bits in, because you can kind of read the bits in, and then the processing of them can be pretty fast, and then writing them back out. Remember, reading and writing to RAM is slow, and so I was actually saturating the bandwidth of the Raspberry Pi, and so figuring out the fastest way of doing the loading was actually really important. So I tried a number of different ways of loading to optimize it. This will copy. So if you have like the value 10 in register 8, this will put 10 into each of the channels of D20. So in that case, you have, it's a D word, so it's 8 unsigned chars. And so this will put the value R8 into each of the channels of D20. Very useful if you're doing like, oh, I don't know, sepia toning. If you want to multiply all of the 8-bit numbers by the same number, you use vdupe and take whatever number you have in R8 and it'll copy it into each of the channels of D20. Then you can do a vector multiply between, do you guys understand? Like, you remember the trick? Like if you want to multiply 0.718 times like some char, like the red value times 0.718, what you can do is you can figure out what that is in terms of fractions of 256. So 0.718 times 56 is 183 or 184, whichever one you want. And so what you could do is you could move into register 8, 184. And then you could vdupe, you could do this command here, and that would put 184 into each of the channels in D20. And then you can take your image data, which is going to be in another register, and multiply it times D20, and then each of those channels is multiplied by 184. Okay? And you're going to want to widen that out to a 16-bit number, right shift it 8 times and narrow, and then put the result back into memory. Okay? And that's how you can quickly do a sepia toning. If you do a multiply by 184 and then a right shift by 8 bits, that's like multiplying by 718. 0.718, rather. Or close enough to it. It's like if I had the number, 100, let's say, times 184, and then I'm going to right shift 8 times, which is division by 256. Then I end up with 71.0 because it's going to throw the last bit out. So I'm going to end up with 71 instead of 72. But if I catch that bit that shifted out, I could use it to round if I wanted. If you want to be more accurate, you can catch the bit that gets shifted out if you want. Let's see. So if you want to saturate, you can use vector max. That'll set Q0 to have the bigger of the values from Q1 and Q2. This one will load, Rivera, you're asking about loading multiples. You can load 1,000 bits. You can load a K at a time, like this. Notice the parameters are backwards on it. So this is going to load from R0 into Q0 through Q7. So it's going to load 1,024 bits all at once. And that's the biggest load you can do. The biggest load you can do is a K in one command. So yeah, so you can do that. You can right shift and narrow like that. And saturating if you need to. More neon. Yeah, you guys know all that. More neon. Yeah, we talked about this. So hard floats means that there is a hardware support for floating point math. If you ever see ABI soft, that means it will emulate floating point math using ints, which is really slow. Yeah. So the running time of these things, multiply is 2 cycles. Division and square root are 14 cycles if you're doing single point. In other words, float 32. If you're doing float 64, division and square root are 28 cycles. And everything else is 1 cycle. Okay. So your fast inverse square root, if you did the inaccurate version, it's 5 cycles. And you could do, if you're using a quad word register, you could hold eight floats at a time? No. Yeah, no. 4 floats at a time. It's quad word. Yeah, makes sense. So you can do 4. So if you use the fast inverse square root using vector math, you can do 4 floats in 5 cycles. It's pretty good. So you can do 4 inverse square roots in 5 cycles. It's pretty good. Whereas that would normally be, what was that, 70 cycles? So it's 10, 14 times faster. Yeah, something like that. Any questions? So ASM demo number 14 has vector math in it, or at least it's not vectors, but it's just doing floats. So we can see what those look like there. I don't think I have anything specifically on Neon, but this is Neon code, right? If you want to make it vector stuff, you would just make this like if you made it a quad register, then it would do, the quad register holds 2 doubles, and so it would do 2 doubles added together at the same time. It's pretty easy. Should probably talk about intrinsics as well. And then 13 also has some Neon stuff in it as well. How you do division, stuff like that. Okay, any questions? Okay. Let's talk about intrinsics then. So you don't have to do Neon in assembly. Well, yeah, true story. You can actually do all this Neon stuff in C and C++. So how does that work? First of all, you have to include this thing here. And what intrinsics do, if they're installed correctly, which they're not right now, you can actually call quad add and things like that. Or not quad add, sorry, saturating arithmetic. So if you wanted to do a saturating add using C++, you can include the Neon intrinsics header file, and then when you overflowed, it would saturate the result. In other words, stay at max int instead of overflowing. Okay. So there's a lot that can be said about intrinsics. Basically, intrinsics are functions. They're functions that take possibly a quad word. Like they create a quad word type, and you can put values into it. But basically, these instructions here look just like assembly, right? And so what you do is you pass it, but it's in C. And what it does, it just generates a assembly instruction for you, basically. And so by using intrinsics, you can write C++ code that is assembly. So do a quad word, shift right, saturating, and narrowing. You can do that using this header here. Okay, so here are the saturating intrinsics. So there's Q add right there, right? So it takes in an int32 and an int32, and it will add them together and saturate the result. So if it was going to overflow, it won't overflow, and it will stay at the maximum. So there's saturating arithmetic, saturating subtraction. I don't know what that is. Accumulating. So multiply and accumulate. So it will multiply A times B, adding C in the result. Okay. Let's see here. Parallel selection. Sum of differences. There's a lot of intrinsics, by the way. Multiply, add, multiplies. CRC JavaScript conversions. Yeah, so there's, if you go through the documentation, you can see basically all of the neon instructions you'd want to do. There is a C++ function for it. And so you can write your assembly code in C++ if you want. It's actually, to me, more difficult than just writing assembly. You can do it if you want. It's sort of for C++ people that think assembly is too hard, and I find it actually harder to write code using intrinsics than just writing the assembly. But it probably might open up some optimizations, maybe. You don't have to know that for this class. You guys understand? Intrinsics? Yep. So basically you just call a function called, I don't think they have the V there. I think it's just add or something like that. Q add. I think they dropped the V from the C++ names. You just pass in the the variables. And they have special variables for doing quad words. You can look into that if you want. If you want to do it for your image filter, go for it. I guess use intrinsics if you want. Like I said, it's easier to just write the assembly. All right, so let's talk big and little endian. All right, so new topic. That's it for our neon talk. Let's now talk about big and little endian, which is obviously a pun. So ARM is bi-endian. Bi-endian means it can run either in big endian or little endian mode. So what does that mean? Okay. So, so the question is whether the first. So when you load an int, where is the most significant bit? Is it in the highest memory address or the lowest memory address? The most significant bit. Is it in the highest memory address or the lowest memory address? And the answer is, in ARM, it depends. Which way is it configured? Okay. So, this used to, well, it still matters, but it used to matter more. Nowadays, it only matters when you're doing networking, because you're not going to notice like which one is at the higher memory and which one's at the lower memory. Like you're not going to notice, because you're just going to do an LDR and it's just going to put the values into a register, and who knows which way they're oriented in memory. Is it top to bottom or bottom to top? Who knows, right? What matters though is when you transmit something over the interwebs. Okay, so when you send something over the internet, by default, not by default, by standard, by convention, by standard, it's mandated that everything transmitted over the internet is big endian. So the most significant bit comes first in big endian. And so this can come back to bite you. If you are on a ARM machine, you can configure it to be either big endian or little endian. But on Intel, it's always little endian. Okay. And so what does big little mean? That's completely different. So big little is a architecture choice, and I think Intel is actually moving to big little right now, or something similar to it. So big little is it has nothing to do with big and little Indian, but just to answer your question. So imagine you got a cell phone, right? And so you got a cell phone, and it's got a battery, and it's got like, I don't know, 3,200 milliwatt amp hours in it or whatever. So you got two different competing needs. One is to have cool fighting games, you know, Street Fighter mobile version. Then you want to have a high frame rate and good graphics quality and stuff like that. And so that's going to require a big, powerful quad-core or octa-core, you know, CPU that guzzles lots of power, and it doesn't matter because you can just charge it, you know, whatever. That's one need. Another need is you're just walking around town. You're not using your phone really. This thing is every once in a while being like, hey, you got any, you know, text for me? Oh yeah, here's a text. You know, here you go. You know, bloop. You know, just like, you know, this does not require a lot of juice or a lot of CPU power. You know what I mean? Like, you know, once every so often, like, hey, I'm alive. I'm right here. You know, talk to the cell phone tower. Hey, you got any messages for me? Any push notifications? No, all right, cool. And so what ARM has is a architecture called Big Little, where you've got possibly some big cores that are used for fighting games and racing games and stuff like that. And then you've got little cores that are used for when you're not in a video game, basically. And what happens is that when you're just walking around town, the screen's off, it'll actually disable these cores, so they don't draw any power. Okay? And so just use the little cores. And then when the little cores notice that their little cores are being at 100% load, you know, when you're loaded, then it wakes up the big cores, and the big cores take over. And so it's an architecture where it'll actually steal, it'll actually be like, all right, move the work over to the big cores and stuff like that. And getting that to work right, it's kind of tricky, but it's really, really important for mobile, because you want a fast, snappy, you know, it scrolls the web pages fast and can run 100 JavaScript scripts from all the advertisers on the web page. So you need both. But if you're running the big core constantly, you're going to run out of power fast. Your battery life is going to tank really quickly. And so Big Little is a CUDA architecture that gets kind of the best of both worlds. And I think Intel is actually adopting it in Little Big Planet. Yeah. Let me just verify that. Big Little. What year is this? Last year. So Alder Lake. So second half of this year, they're going to release a Big Little core. All right. So there you go. Good. Considering all these talks get recorded on YouTube, it's always embarrassing when I remember something wrong, right? Okay, so Big Core is using Big Indian. Nope. Big Little has nothing to do with Big and Little Indian. Okay? So the only time this is going to matter to you guys is if you take an architecture class and they quiz you on it. Big Indian calculator. Let's see if we can visualize this. Online hex converter. Hex string input binary. Okay, so hex values. Okay, so FFAA77CC. Let's see how this works. Error with the input string. Really? There we go. All right, so you can see and zoom in. So FF, as you can see, is 8 ones in a row, and then the A's are 1010, 1010, 77, and then CC. So if this was in Big Indian, the most significant bit, you know, the first one, the one that's the most important, comes first. In Little Indian, it's backwards, right? So it goes CC, 77, AA, FF, right? So in Little Indian, it's the other way around. And, yeah, these aren't used. And so the, do you guys understand? Like, like when you're looking at RAM values. The only time this is going to matter is if you're loading like 1 byte at a time and you actually see what order they're stored in. Is it stored like this? Like when you read the first byte of a float, is it CC or is it FF? Right? That's the only time it's going to matter. And since you're going to be loading a 32-bit number using LDR and loading 32 bits anyway, it would be unlikely that you would see this. But if you did do an LDRB 1 byte load, then you can find out, is it big endian or little endian, right? Am I going to get CC or am I going to get FF? And it's just the order that they're stored in memory. It used to make a difference for architectures. I think Intel picked little endian because it allowed one of their wires to be shorter or something like that. Like when they were designing their registers, I think, like they had a thing, and if they flipped it around, the wire could connect easier. And so that's why we've had this bifurcation in the industry for 50 years now. If you were to just take a int or a float and transmit it over the internet, you would be wrong. You would be wrong. And the reason for that is because the reason why it's wrong is because the internet mandates big endian. So the most significant bit comes first. And so man, host to network long, network to host long, network to host long. There we go. If I can spell. So ARPA, yeah, that's how old this is. Because C++ does not have a networking header file. Come on, guys, it's 2021. Come on. They're working on it. It's a tough thing. The internet's been a thing for 50 years now. It's almost ready for standardization. So we still get to use the old C header files for doing networking, unless you use some non-standard things like Boost has some decent libraries and things like that. But yeah, if you're going to use the standard library, you're going to be using ARPA, because the internet was originally called ARPANET. What? Yeah. What is ARPA? The Advanced Research Projects Agency. It's part of the military. The internet was designed to survive a nuclear war. The internet came about because they wanted to connect together different parts of the country so that if the Russians nuked our country and took out a communications line, the internet could route around it. That's where the internet came from. The internet protocol was designed to be tolerant to nuclear weapons. And it was a project from ARPA. And so the first internet was called ARPANET. I used the internet back in the day when it was still called ARPANET. That's how old I am. Actually, I was pretty young at the time. But it's not like I used it. Seriously, I went on there and I'm like, yeah, okay, there's absolutely nothing for me to do because I didn't know anyone. Like, who am I going to email, right? Or any games, or any of that stuff. So here is the ARPANET in 1977. This is the entire internet, by the way, 1977. So you got MIT, which had a bunch of where's MIT? UCLA, UCSD should be on here too. They're one of the early ones. USC was connected to UCLA. And these are the machines. This is actually a list of all the machines on the internet. So PDP 11s and 12s, this is what like C and C++ were developed on. Back in the day, they were like cheaper alternatives to IBM mainframes. New York University, Rutgers, Aberdeen. Where is MIT? University of Texas, Rand, Stanford, Hawaii, over satellite. That's cool. There's MIT. Yeah. So MIT had some of the most, had like, MIT used to have 1/256th of the internet addresses. Did you guys know that? So back in the day, MIT was allocated one of the first octets. So like 41, all addresses beginning with 41 was MIT. And then over the years, they've had to give up most of their internet numbers because there's not enough internet numbers to go around these days. There's more people than there are internet numbers, right? So, this is ARPA. Yeah, now it's called DARPA, which I think was a dumb name change. You know what I mean? DARPA. DARPA. Right? So it's now DARPA. It was renamed in the 90s, I think, right? When did it rename itself? It doesn't matter. Anyway. So that's how old this is. All right, so if you want to transmit something over the internet, you need to convert to network byte order, which is big Indian. Okay, so if your machine is little Indian, it will break when you transmit to somebody else over the internet, and it'll break. Probably, who knows? Maybe they have the same bug. If you wrote both sides of it, you might not notice that it is broken until you try connecting to a machine that is big Indian, and then the big Indian machine is going to be transmitting bytes to you, and everything's going to be coming in the wrong order. So every time you do something on the internet, you must convert between host, your machine, to network, and that will convert from little Indian to big Indian. If it's big Indian to big Indian does nothing, and it just returns the value. And so it's always safe to call network to host long and host to network long, because it now does not matter whether your machine is big Indian or little Indian. The number is now suitable for transmission over the internet. Okay, so anytime you transmit something over the internet, any integer or whatever, you always convert it to network byte order, even if you're on a big Indian system, because who knows, maybe someday they'll port your machine to an Intel machine, and then your code breaks, and that's terrible. You port your machine, everything compiles, it runs, but the person appears in the world and they're just flying around like this. You're like, what the hell is happening? The person's like, and it's because the location is being transmitted to you in big Indian, and you didn't convert from big Indian to little Indian, and so all the bits are backwards in your location, and so they take one step and it teleports them to the other side of the world or whatever, right? So anytime you work with sockets programming, you need to know about that. DARPA. Such a dumb name. So, yeah, up in the works for 2023, though. They're talking about doing networking. So, yay, you go, guys. You're almost up to the mid-90s. Maybe someday we'll have graphics support in C++. That would be cool. To draw a window. That'd be nice. I hear that mice are things, like computers have these things called mice. That's cool. Maybe we should support that at some point. I don't know. You're confused on big Indian and little Indian. Sure. So let's say, Mammy, let's say that you want to save 1, 2, 3, 4. Let's say you're going to write this number. Let's say you have this number in memory. FF 771100. So these are all ones. These are 0111, 0111, 0001, 0001, and all zeros. Okay. So these are 4 bytes. This is a 32-bit number. It's 4 bytes. The question, Mammy, is let's say that this number is at address 5000. Okay. Is the most significant bit the FF? Is that the first byte, or is it the last byte? On a big Indian system, the most significant bit comes first. On a little Indian system, it is in the opposite order. So it'd be 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, so on a little Indian system, the least significant byte comes first. On a big Indian system, the most significant byte comes first. And so it's just a matter of how they're laid out in memory. Does that make sense? And you haven't had to know this your whole life because it doesn't matter. If you do an LDR, after you load this from RAM, it will be the number, right? So yeah, it's just a matter of order. It's like, how is this held in memory? The only reason why this matters at all is because when you transmit something over the internet, if the other guy, let's say the other guy's a big Indian system and you transmit 0000, 001, 001, then they read all the bits backwards, right? And so they get the opposite, like they get all the bits in the opposite order. And so there is something called, there is something called host 2. I don't know why I was spelling it as OT. Host 2 network long, and there's network 2 host long, and this will convert. It takes in an int and it returns an int. And what it does is it just puts the bytes in big Indian order. And then network to host long does the opposite. It takes the ints. This is going to be a big Indian int, and this could be any Indian. And so network to host long does the opposite. It takes in big Indian, and then it returns whatever Indianness you have. So these functions you have to know if you're ever going to be doing sockets programming, network programming, which I'm hoping to get to. Every year I try teaching sockets programming, and it always is a train wreck. So I'm hoping to get to it this year. But I want to do hash tables also. So the next homework assignment after the image filter is going to be hash tables. So Battleship 2.0, yeah. We didn't get to hash tables either in 41 or 26 last year. And so you guys need to know hash tables. So you're going to implement a hash table in assembly. It's not too bad, actually. I think. I haven't done it yet, but I assume it's easy. Okay. I assume it's easy. I'll give it to you guys, and then we'll find out. So it'll be kind of like a programming competition to see who can have the fastest implementation of a hash table. Please don't just implement a hash table in 26, then it's fresh in your memory. Yeah, these guys, normally I do hash tables in 26 and in 41, and the rest of these guys haven't had it at all. You did hash tables? Yeah. Did you? I mean, you used them. Did you make one? Did you implement one? Did you do double hashing? Yeah, we talked about it really briefly in 26, but, well, you made one for the caching worksheet, yeah. So anyhow, you'll whether or not you guys have done hash tables, you probably haven't done hash tables in assembly, so I'll hack that out over the weekend and give it to you. That will be your last programming assignment? No. Okay, so last. It's week 10, dude. We got like 8 weeks left or something. Okay. There is a lot of programming to go. I do want to do networking, and for the hash table, you can do any kind of hash table you want. It's my plan, but it has to be in assembly. And you're going to be graded on how fast your hash table is. Okay, so not quite ready to talk about memory management yet, or that. Let's see. We talked about classes before, throwing a class in assembly. Let's see if there's anything in here you need to know. Code tennis. Yeah, we've already talked about this. Let's go over this. This will be good for the rest of class. Okay. So one of the things that hopefully you guys are picking up from this class is like how to make files and linking and the difference between linking and compiling and assembling, right? Are you guys kind of absorbing at least a little bit of that? Like Muya the other day asked me, when you compile a code with -03, what step does the .o go on, right? So if you've got, let's say you've got a.cc and b.cc, one of the steps in your makefile is going to turn that into a.o, one of them is going to turn that into b.o, and then these things are going to get linked together to form an a.o, right? So where do you put the -03? And the answer is in all of the steps. All the steps. So you do g++ -c -03 a.cc. That would convert from a.cc to a.o. And then when you link them, g++ -03 a.o, b.o, and that will make the a.o. Yep. So this lecture, though, is going to kind of go over all those steps formally, so you guys can finally understand what's happening when you compile something. When you type make, what happens? Okay, so there's more than 4 steps. There's more than 4 steps, but we're going to talk about the 4 big steps. Okay. There's the compiler. The compiler step is more than a step. You know what I mean? It's like the preprocessor, and that's a whole separate program that runs. Yeah, and then we got 40 minutes left. Yeah, we should be able to get through that. We might talk about the difference between static and dynamic linking. So, linker errors are one of the more annoying things to deal with in computer science, and after this class, you should be able to recognize them and fix them. How many people here have seen a linker error before? So like here we got class.cc. It's going to call some function called mess with ssint, right? It's got main. All right, cool. So if I just compile class.cc by itself, linker error. And the reason for that is because this code is calling mess with the social security number thing, but it didn't find it. There's no where is it? You know, where is that? You know, and so there's a .o file somewhere in here. You know, yeah, there it is. Right, and so if you don't link those things in, then you get a linker error, which means that it's calling a function, but it can't find it. And linker errors look different from a compiler error. Compiler errors these days have nice colors, you know, things like that. Linker errors look like they're out of the 1970s, because they kind of are. And so you can tell it's a linker error because it says this. Undefined reference, yeah. Anytime you see undefined reference, you got a linker error. Because the linker is trying to find all the functions you promised exist in your colon. But if it can't find it, then it spits out a linker error. So a linker error, you can tell it's a linker error because that LD is the linker. I don't know why it's not ln. Maybe because ln is the symlink command in Unix. The linker is called LD for whatever reason. So inside of this file, you notice that that's a temp file. The reason for that is because whenever you compile from a CC, it makes a .o file. It just deletes it afterwards. So that's the .o file. Cool. Inside of the function main, at this offset, it tried calling delete BS, and it tried calling mess with ssn, and it couldn't find them, and so it quit. So collect2 is the name of the overall suite, I guess. So collect2 called the linker failed. You did not get an executable. Sucks for you. Okay. So that is what a linker error looks like. It looks like scary. So remember the acronym CALL. Compiler, assembler, linker, loader. Those are the 4 big steps. And each of these big steps will oftentimes have smaller sub-steps as well, like the optimizer, for example. Okay. Tinker, Tailor, Soldier, Spy. Yeah, exactly. Not your knowledge of assembly. What's the matter with your knowledge of assembly? You know ARM32 assembly. You got it, I think. You know, it's just adds and moves and compares and branches. That's about it. Yeah. So you just got 5 or 6 different commands you got to know and put them together and organize it. Oh, the linker that still works somehow. Yeah. Okay, so here we go. So step 1, compiler. Step 2, assembler. Step 3, linker. Step 4, loader. All right, let's do it. So let's say that we're going to compile this source code. We got main. Inside of main, we got add the sign of 0 to the cosine of 0, so it should return 1 or 1-ish because we're working with floats, right? So what happens when we compile the code and we run it and we get a 1? All right, this is CSI 40, right? So, this, where's my mouse? There it is. This is how things work in CSI 40, right? You make a .cc file, hashtag include math, main int main, cout sine plus cosine, compile it, run it, it prints 1. It's a simpler time, more peaceful time. Before you knew what was actually happening underneath the hood. As it turns out, it's actually more complicated than this talk will even reveal. So you can actually dig pretty far down to actually figure out exactly what is happening here. I took 2 quarters of compilers just to learn the basics of how compilers work. I had friends doing compiler research stuff and like on the optimizer and stuff like that. And then when you get into like the details of like linking and you can really get into the weeds and really get into the details of what's actually happening. But I think today's lecture will give you a good high level view of what's happening. Lower level than CSI 40, higher level than what's actually happening. Okay. So, time to pull back the curtain. Okay, let's find out what's happening. So, you type compile, boom. So, when you type G++, G++ isn't actually a compiler. It's the GNU compiler collection. GCC is the GNU compiler collection. And it is actually a suite of tools. It's a bunch of different tools living under one roof. And so that's why you notice that I just use G++ instead of AS, to do my stuff, because the G++ is smart enough to figure out what it needs to be doing. Should I be linking right now? All right, call the linker. Now, should I be assembling right now? Call the assembler. So, I just call G++ over and over again, and it's smart enough to figure it out. So, there are many different things, like you just saw collect 2 in that previous thing. The C preprocessor is called CPP, which is an unfortunate name, because that's also the name that Windows people use for .cc files, right? You have CC1+, which is the C compiler, or the C++ compiler. AS, the assembler, LD, the linker, LD.so, the loader. There's a lot of different tools that are all kind of under the hood that sometimes will pop up, like with the linker error. It's like error in LD. What the hell is LD? It's linker. Right. So, if you don't link in the math library, it won't work. What? You have to link in the math library? Sometimes you do. Sine and cosine are not in the standard library. They are held in the math library. And so, depending on how you have the linker and loader set up, sometimes when you compile your code, you would have to say G++ main.cc-lm. And that will link in the math library. I have it set up to do it for you automatically. So you've probably never seen that before. But if you go on to other systems that have their linker and loader configured differently, congratulations, you will get a linker error trying to compile and run code with a sine or cosine in it. Even if you include the header file. The header file is not a library. You have to do a -lm. Okay. Yay! Okay, and so each one of these things can cause different errors. And they all look different. Right, so if we come back up into class.cc, and we, let's see if we can include CMath. So let's see what happens if we do this. Okay. So that would be, it's colored nicely, so that might actually be the compiler that picked that up. But so you can have mistakes in your preprocessor that picks up. The C compiler obviously picks up mistakes. The assembler is probably not going to pick up mistakes unless you're writing assembly code. If you're writing C++ code, the C compiler will generate assembly that will compile, unless something goes horribly wrong. Like if you do inline assembly, maybe, then you can get an AS error out of that. And then if you don't link your code properly, you're going to get a linker error. So the good news is most of the errors you're going to get in computer science are compiler errors, and hopefully by fourth semester computer science, you guys have seen lots and lots of compiler errors, right? You guys understand? Like most of the problems you're going to have when you're working with C++, it's going to be a compiler error, right? You should get experience with compiler errors. If you write code that is too good, you should write some bad code, just so you can see what a compiler error looks like. Okay, so the compiler phase is actually split into more parts than this, but we're simplifying. So the C preprocessor is called CPP. You can invoke it using -E, capital E. And so if you wanted to see what, let's see, I logged out, dang it. So if you want to see what the results of the preprocessor are, you can do so with -E, cd into asim demos g++ -E class.cc. And you can see pipe through word count. So there were 63,000 lines of code in a file that is 73 lines of code. So my code is 73 lines of code. With those two simple little headers that I've included, it is now 64,000 lines of code long. Okay. So this is what it actually looks like when you include something. All this stuff gets included. All this stuff gets included. Okay. And you can notice, look, hard floats. Hard floats. Okay. Hard float. See how there's a GNU extended ABI hard float? Those things might actually start meaning something to you now. GNU is the GNU project. The GNU project is free and open source heroes of the free world. ABI is the application binary interface, and it is using the hard float application binary interface. Why? Because like it said on the slide that I didn't read to you, if you are calling hard floats and soft floats, your code won't link together. There's actually a separate ABI for using hard float math and soft float math. Okay. So your code won't link if some of them are compiled with hard floats and some of them are compiled with soft floats. Soft floats means you don't have a neon or you don't have a floating point unit. And so it has to emulate it. And so good. It has detected that we have neon and we have hard floats, so that's good. And then if we scroll down through here, you can see all of the IO stream header is now copied and pasted into our source code. Here is our beautiful, beautiful source code. This is all just header file stuff. All header file stuff. Okay. What would your compile time look like if you included the whole STL? Let's find out. You want to see? You want to see? C string. Yeah. C string. Nice C string in here. Oh, it's got stirred copy. Yuck. Do you guys want to include the entire standard library? So it is called bits. Bits. Standard library. Bits std C++. So some students are not diligent students, and they will do this. And if you do that, you don't need to include any of the standard headers. This one trick that doctors hate includes the entire standard C++ library. And if you do that, pipe through word count, you can see that we now have 250,000 lines of code where we had 65,000 before. And as you can imagine, this will slow down your compile time. Now, sometimes it might speed it up. Why? Because if you use what's called a precompiled header, you can actually precompile all of the standard library headers. And so sometimes using bits is actually faster. If you're including lots of header files, then having one precompiled header that you don't have to rerun the preprocessor on every time is actually really nice and can speed up the compile time. Mostly, though, people use this because they're lazy. They don't want to have to hashtag include CMath and hashtag include CString. And let me get rid of this. Um, let's see what kind of difference it makes here. Feel that compile time? Feel that compile time. Yeah. You guys see that? 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5. Yeah, that was 256,000 lines of code that it was chewing through right there. Okay. Okay. So that's the include everything header file. And some students will do that because they just don't want to, like, where's tuple? It's in hashtag include tuple. Oh, okay. Where's pair? It's in hashtag include utility. Wait, what? Yeah, pair is in utility. Where is deck in Q? Where is the binary search tree? It's in set. And so they don't want to have to look it up or stuff. So some of them are lazy and they just do that. But it hurts your compile time performance. Sometimes. Most. Maybe. Try it out. See if it works for you. It's also common in coding competitions because in a coding competition, you're trying to optimize your time, right? And so you just slam that down. First line of code, all your headers are included. Go. You know. So, all right. Coming back up to here. So yeah, if you're ever curious what the preprocessor is spitting out, -E will print it to the screen. And if you want to see the results of your assembly or the compiler goes and generates assembly. You can do the -S, which is really useful in this class because if you ever forget how to do something, just do it in C++, compile with -S and C. Just remember, though, I do actually spend quite a bit of time looking through students' assembly code, and if I see that you have a compiler-generated assembly, you get a 0. It is technically cheating to copy from the compiler, but if you just like forgot the order of like, you know, is it, you know, what order do these things come in? It's a cheat sheet for yourself, you know, but don't just copy blocks of code. It's blatantly obvious when students copy from the compiler because the compiler doesn't generate human-like code. It'll keep reading and writing to the same register over and over again, and it looks really bizarre. It's very obvious when students cheat that way. Fortunately, nobody really does. Okay. All right, so yeah. So the C preprocessor, any line of code that starts the hashtag is a C preprocessor line. We've talked a little bit about this before, so I don't want to belabor the point. Last time we talked about -D, right, in the make files. So that if you say in your makefile, if you -D TD equals 6, that will define TD to be 6, and then anywhere in your code, if you coutted TD, it would print 6. 6 points for a touchdown. Okay. So it defines a constant, a C-style constant. You can check to see if something is defined, and if it's defined, you can have one block of code for Linux. If it's not defined, have a different block of code for Windows or a different block of code for Mac OS or whatever. And then just remember that your if statements always end with a #endif. So C++ has been working to get rid of the C preprocessor as much as possible. This is the current thing on the chopping. These things you can kind of do away with already, but include. That is the big thing on the chopping block right now. They're moving to something called modules. That is in C++ 20, but support is not actually implemented yet. G++ 11 will support modules. G++ 11 should be coming out shortly. So pretty exciting. So maybe you can start writing code that doesn't use #include. Kind of cool. I'm sure Marshall is working on it right now. Why 11? It's just G++ 10 is the current G++ compiler. The next version of the G++ compiler will support modules. How will modules work? I'll tell you later. Nobody really knows. I mean, there's a standard for it, but how they're actually going to work in practice, we're all just kind of like, it's coming. It's coming. We'll see. We'll probably have a lecture on that at some point. Okay. Hopefully it'll come out before the end of the semester. If not, you know, I don't know. Okay. So the compiler, CC1 is the C compiler. CC1 plus is the C++ compiler. That is an error. Okay, so CC1 plus is the C++ compiler. CC1 is the C compiler. And so what a compiler does is it takes as input source code and it outputs assembly. So in phase 1, we have the preprocessor takes a .cc file and it produces, well, another .cc file, right? So the preprocessor, it's called CPP, the C preprocessor. The C preprocessor modifies the .cc file. And it will add code, remove code, whatever. It modifies. It's a programming language that runs on your source code. It's kind of cool. You do a lot of macros and cool stuff like that. Some, like Unreal Engine, uses the C preprocessor heavily. Qt, the kind of de facto UE standard for C++, uses the preprocessor heavily because there are things the language can't do right now. And so the compiler, CC1 or CC1 plus, CC1 plus is going to take your source code and make an assembly file. That's what a compiler does. A compiler translates between source code and assembly. That's it. That's all a compiler is. Okay. You guys understand? So the compiler phase of this whole thing is just going from a .cc file to a .s file. That's it. It's a big step, and there's a lot of parts in it. But that's it. Like when we say compile your code, the compiler part is actually one of the steps. You guys understand? So the final part of the compiler is the code emission, where it generates assembly. But there's a lot of steps inside of the compiler. There's the lexer and the tokenizer and lexer, parser, optimizer, intermediate code generation, sometimes in there before the optimizer if you're in Clang, and then finally it emits assembly code. The last step of the compiler is to just emit assembly code. That's its job. The C++ compiler's job is to take in a .cc file and produce an equivalent .s file that does the same thing. Okay. So, okay. Register allocation's annoying. Optimization is complicated. You can take a whole class on that, grad class, just on optimizing. Okay. Then the next step along the way is the assembler, AS, is going to take in a .s file. So it's going to take that .s file in, and it's going to turn it into a .o file. So the compiler gives you the .s file, and then AS is going to convert the .s file into a .o file. And it's usually pretty straightforward. The assembler, more or less, just goes through all the commands. Like if you say add R0, R1, R2, it's got some, there's some reference manual that says add is command number 4. Okay, cool. And so all the assembler is going to do is just translate this assembly command here into zeros and ones. That's 90% of what it does. Okay, so if add is command 4, then it would be like 0, 0, 0, 1, 0, 0, and register 0 is 0, 0, 0, 0, and register 1 is 0, 0, 0, 1, and register 2 is 0, 0, 1, 0. It's a little more complicated than that. There's actually a format that I don't have in here. There's actually there's documentation that tells you what all the bits need to be. But basically all the assembler does is it just takes a line of assembly and spits out the zeros and ones corresponding to it. And it's actually pretty easy to write. Like you can write an assembler really easily because you just got your documentation. You know, subtract is command 2, and multiply is command 7, and you know, I've got the breakdown of it. You guys care? I don't know if you do. Here. Here's a graph of the whole thing. Programmer edits source code. Compiler turns it into assembly. Assembler turns it into .o files. The linker turns the .o files into a .out, and then the loader loads it into RAM and runs it. So that's what we're talking about today. Where is the picture? There you go. So this is the actual in the documentation. Like, and I dug around in the ARM documentation, I found it. And so when you have like an add instruction, opcode, an opcode is like, you know, 0001. What does that mean? Add, or whatever. And if the opcode is 0011, then the opcode is, I don't know, subtract. You guys understand? So there's only 16 different opcodes. It's only 4 bits. So there's only 16 different basic commands in ARM32 assembly. Now, you might be like, what about add and set or move if greater than and things like that? Well, that's these 4 guys up here. So those bits, if you have like add and set if greater than, then these bits, you know, whichever bit is for set, whichever one for greater than would be set there. Okay. Destination register, source register, and then the flexible second parameter. The flexible second parameter can either be a register or a constant, possibly with a shift on it. You guys understand? So when the assembler takes the command like add and set greater than R0, R1, 7, it just has like a table, and it's like, okay, add is 0001, so these bits are set to 0001, and it's got a set, and it's got a greater than, so that's 0101, and these are always 001, and oh no, that's the set bit there, sorry, so that's 1, and the destination register is 0, so that would be 0000, and the source register is 1, so that'd be 0001, and then for the flexi parameter, it's going to be 7, so that'd be, I don't know, 0111, something like that. Okay. So that's all the assembler does. It just translates, it just spits out bits, okay, with a little bit of intelligence, okay? And the little bit of intelligence, is for things like push and pop. Like those aren't real commands, right? So push, pop, they're called pseudo instructions. Push and pop, and LDR. So it actually generates assembly for you. So if you say push these 5 things, it'll generate a assembly code to push them into the stack for you. There's a couple things like that, and the assembler has aliases. You can make variables like pi. You know, and it's got macros. So there is a little bit more that the assembler does, but its basic job is really straightforward. Like I met a guy who wrote an assembler for an IBM mainframe, and I was on a train ride with him, and he said, "Yeah, I was just on a train ride like this. I borrowed the documentation," and I'm like, "Oh, well, okay." So branch is 0001, okay. And so if I get a branch instruction, I'm going to output 001, and then I'm going to jump to this row. So that's okay. You know, and so he read the documentation, just wrote an assembler for it. It's pretty easy. Okay, so yeah, LDR, push and pop. So the actual assembly for push and pop is to store multiple increasing stack, empty or full stack, you know. There's like all these different options for pushing and popping off of the stack, and the simple way of doing it is just use push and pop because it generates the assembly for you, so you don't need to worry about it. It can align numbers for you automatically. If you do ASCII Z, it'll add a null character to the end of a string for you. Yeah, if you do the data, if you have data or text, then it will put them into the right segments. there is a little bit of intelligence in the assembler. More or less, though, it just does a bit-to-bit conversion. And if you really are cool, you can actually compile x86 on ARM. So it's called cross-compiling. So for example, if you've ever used an Arduino is using it uses a really cheap CPU that can't support a compiler because it doesn't have enough RAM on it. And so what you do is it's an Atmega chip. It's got like, I don't know, 16K of RAM or something trivial like that. It cannot support a compiler. So what you do is you compile the code on your x86 machine, telling it to emit assembly for the Atmel chip. And then the Arduino Studio does all that for you. You don't see it because it's designed for kids. So what happens, you write your code in for the Arduino on a laptop, and then you hit compile, and it compiles it, and it generates assembly for a different architecture. And it can do that because all you're doing with an assembler is there's just a table, right? Maybe on a different architecture, add is 20 instead of 4. You know? And so it just has a table, and just uses a different table and emits different assembly code. Yeah, more or less. So, okay. And then the Arduino Studio transmits the object code to the flash memory on the Arduino, and then it hard resets it, and then the Arduino grabs its program from the flash memory and runs it. So, okay, so step 3 is the linker. So the linker is when you've got all of these different .o files. This function is here, this function is here, and it puts them all together into a a.out. Okay. So it's going to let's see if I have a picture of it. Yeah, so let's say you've got main.cc, and main.cc is calling sign, like we talked about before. So sign would be found in what's called libm.a, or it might be libm.so. And so you've got your main.o, and main.o is calling sign. And I've shown you guys this before. When you use nm on a .o file, it will tell you which functions can be found in that file, like main is found in class.o. But then it's calling string copy. String copy is not located within class.o. It is undefined. And it's calling asim mess with ssn. It's not in here. And so what happens when you call the linker, if we nm, what was the name of the thing? Delete bs. If we nm delete bs.o, we see that there is a function called delete bs. And so that function is going to be called from here somewhere. Did I miss it? It's supposed to be in there. I don't know where it is. And then if we look at, what was the other one? I don't remember the name of the other one. 19 class. Okay. So if we g++ 19 class -c, and we nm 19 class.o, you see that this function here has asim mess with ssn defined in it. And so when you link the things together, if I say link together, and I'm just going to call the linker using g++ as normal, 19 class.o and class.o, then what happens is, maybe I remove the reference to that, because you can see in here it's not actually calling it. So, so this guy has a hole. It's got a jigsaw piece missing. And that jigsaw piece is called asim mess with ssn. And you can see it's undefined here. And then in 19 class.o CMUI, you can see that it is defined here. And so when the linker links the two together, it finds that missing jigsaw piece and it puts it in, and then builds an a.out named a.out. And you can see that everything is in here. Asim mess with ssn is defined, main is defined, start is defined, end is defined. There's main, everything's happening. Okay. But you might be like, wait, string copy is still undefined. Yep. And the reason for that is because it is in what's called a dynamic library. And we'll talk about that next time. Okay. So anytime you see an at like that. That means it's in a dynamic library sometime, and when you run the program, that's when it finds it. So we will pick up this lecture on Tuesday. In the meantime, get sepia toning done by tomorrow night, and then make an artistic assembly filter. You're going to be judged purely on artistic merit. So make it look good. Okay. And that will be cliffhanger. I know. But it's important stuff. It's important stuff. All right. Peace out, you guys. Thank you.